Okay, everyone, thank you for coming. Settle in, I have some notes. So we've asked Isaac to keep this short so that we can have a very long introduction. So Isaac is from New Hampshire, correct?
Yep.
Born and raised. Went to school there at the University of New Hampshire in mechanical engineering. Came to Virginia Tech and joined mechanical engineering as well. And he originally was working on combustion. Why he left that and came to the light side, I'm not sure. But in around 2013, 2014, he joined our NSF iGrip program, the multi-steps program. And as part of that, he did a rotation in my lab, in Shane Ross's lab, and David Schmalley's lab. And afterwards decided that he actually wanted to work on flying snakes. So Isaac was most interested in dynamics and the theoretical side of things. So it took some convincing, in fact a lot of convincing, to get him to be able to do experiments with the actual animals. So we convinced him that his work would be a little more interesting with the animals. He was also very interested in getting out of here as fast as possible. So this is one of his objectives, and this slowed him down a bit, but hopefully, as you'll see, it has turned into quite an interesting story. So Isaac really took this and ran with it, and he's really done some very excellent work. One story to characterize Isaac and his behavior. So one day I had a knock on my door, and it's Isaac. He comes in. He's got a stack of papers with him, and he hands it to me, almost like an offering. I said, "What is that, Isaac?" And he said, "That's a manuscript." And I went, "Manuscript? I didn't know you were writing a manuscript." He handed his advisor a manuscript without asking, a whole manuscript. You can't imagine how surprised I was. Isaac's surprise came in the 35 drafts that came afterwards. Didn't get published afterwards. But the paper was published at Bioinspiration and Biomimetics, and it was actually just named one of the 10 highlights for the journal for 2017, highlighting its excellent work. Lastly, Isaac gives very, very good presentations. No pressure. Testament in 2 awards. So one was at a Dynamical Systems conference. He won the Red Sock Award. I have no idea what that is, but apparently it's a very good award. The other award was at the Society for Integrative and Comparative Biology conference. He was in the talk competition for the Division of Comparative Biomechanics. To get into the competition itself is difficult. And then there are 8 students who go up and present, and they all give very, very good talks. Isaac won the competition and the award, and then he's off and running. Lastly, he got hired recently at the Applied Physics Lab of Johns Hopkins, and apparently they like him quite enough to be able to give him all his demands in the negotiations without having any counteroffers. That's how badly they wanted Isaac.
Or how badly you negotiated.
With that, I turn it over to Dr. Ross.
So Jake and I co-advised Isaac. I would have thought that Isaac was looking forward to a life as a lobster fisherman after this. Let's see. But no, he's been, so as you'll see, he combines experiment and computations in a very excellent way, I think. And it's been pressure from both of our sides, the experimental and some modeling, and then mostly modeling from me. So this is the timeline. Isaac has requested that you save your questions until the end, unless they're very pressing. So that'll take, we think, about 45 minutes, possibly. And then there'll be questions from the non-committee members, and then we're going to ask the non-committee members to leave the room, and there'll be a closed-door session with just Isaac. And then his fate will be determined. So with that, I hand it over to Isaac.
Great. Well, thank you for the introductions, and thank you all for coming. So today I'm going to talk about some of my PhD research looking at this animal here. So this is the flying snake, Chrysophila paradisii.
Did you guys hear in the back?
And what makes these unique animals is that they can jump, flatten their bodies, and undulate through the air. So this is a unique form of locomotion. And you can see it's quite visually striking. So the tail is whipping around here. You can see that there's quite a bit of out-of-plane motion of the snake's body. It's maintained its head control throughout this whole event. And it's short, so here the snake's getting ready to come land. It lands with its posterior body first, and then it's going to re-round. So what I'm interested in is how this animal undulates through the air and why it undulates through the air. So the scientific motivation, so there's a couple. One has to do with looking at gliding animals in general. So gliding's evolved numerous times in diverse things such as frogs, mammals, some lizards over here, insects, squid and fish can even glide. So it should give these animals some advantage. Otherwise, presumably it wouldn't be there. So we're going to understand the mechanics behind that. And then the second scientific motivation has to do with the evolution of flapping flight. So that's a very rare event. It's only evolved 4 times. And so the hypotheses about for the origin of this is that there was some gliding intermediate, right? So you went from a static wing configuration like we have here to some oscillating wing like a bird. So that doesn't exist in the fossil record. So maybe by looking at gliding animals, that can give us some insight there. And of the gliding animals, the flying snake is the most dynamic. The engineering motivation would have to be bio-inspired snake robotics. So this idea has been around since at least the 1970s, and snakes are good targets because they're slender body profile, so they can get into tight spots. Their gaits are stable, so it's not going to tip over on you, and it's fairly energy efficient. And there's been some really nice work recently on extracting biological waveforms, in this case from a sidewinder, and programming those into your snake robot. So in this case, the robot can now move up sandy hills and turn on sand. And then you can use the robot to test some biological hypotheses. So this wasn't the main motivation for my work, but I think some of the work I'm going to talk about will speak to this. So my talk is broken down into 3 sections based on the 3 papers in my dissertation. So I'm going to briefly talk about some modeling work, so a general mathematical framework to analyze gliding. Then I'm going to spend quite a bit of time talking about the snake and some glide experiments as well as some modeling. And then lastly, the forces and the body configuration of the flying snake. Okay, so when I first began looking at gliding animals, I was struck by the morphological variation that you see. So all of these gliders, they look quite different, but the underlying physics of gliding is quite simple. You have a body falling through air, and it's going to use some sort of wing-like structure to push against the air and to move horizontally. So the complexity we see, so the different wings we see, that's really just going to affect the lift and drag characteristics. So I thought there should be some nice way to analyze gliding in a very general way. Another issue I had was how they were comparing glide performance in papers. So often they would look at the vertical distance versus the horizontal distance, and they would make the equilibrium assumption. So on this view, gliding equilibrium is going to be a straight line. And this is the static case where the lift and drag balance the weight of the glider. And what's nice here is the lift to drag ratio determines how shallow that line is. So a higher lift to drag ratio, a better glider. However, when you actually look at animal trajectories, you see not many straight lines. Right? So there's a transient event here that's important, and then even later in the glide, they don't appear to be reaching equilibrium. So I wanted to address this. And so what I did is I developed a model to kind of get rid of all the animal-specific complexities. So it's really easiest to think about this as a flat plate glider. So this flat plate, it's going to have some lift and drag force and the weight acting on it. It's going to evolve in the vertical plane, so the glide angle is going to change as well as the velocity. We're going to control the rotational motion of our model, and that's ultimately going to affect the angle of attack and the forces acting on it. So the equations are simple enough to write for this system, here in Cartesian and polar form. But the key takeaway is that the lift and drag characteristics, the coefficients, are the only animal specifics in our model. So using a new rescaling, we got rid of all the animal size effects. And it's important that these are functions of angle of attack, which generally hadn't been done before for gliding animals. And then lastly, we have the pitch angle here. So this is our only model input, and we treat this as a bifurcation parameter to elicit different system responses. And something else in this work, I introduced the velocity polar diagram to analyze gliding animals. So instead of looking at the vertical and horizontal positions, we're going to look at their velocities. And so the way you read this along the exterior, these are the initial jump conditions. So the ones in black are what you would see in an organism. We have the arrows here indicate trajectory progress and forward time. Equilibrium is now a point instead of a line. And you can easily read off the airspeed as well as the glide angle at equilibrium or at any other location in the velocity polar diagram. And the reason we like this view of gliding is that it shows structure. So there's this common feature. We termed it the terminal velocity manifold. It's like a high-dimensional analog to the terminal velocity. So trajectories will come to the manifold quickly and then move along it slowly. So I'm going to demonstrate this model with the flying snake cross-section, but in the paper we used a variety of different gliding and flying animals. So this is the velocity polar diagram for the snake in a pitch-down configuration. This is horizontal, and now this is pitch up. And so although the pitch angle only varies by 10 degrees, we see different behavior from the model. So the top two look pretty similar. We have one equilibrium point, and we have the terminal velocity manifold. But something different going on down here. In this case, a separatrix appeared, and this is going to distinguish initial conditions which give rise to bad glides, that'd be like falling, or to good glides where the glide shallows and reaches an equilibrium state. And I summarized these in what I call pitch bifurcation diagrams. So they show the equilibrium glide angle as a function of the pitch angle, and the number and stability type of the different pitch configurations. So it's a way to kind of summarize the different behavior that we see. So in summary, from this work we found multiple modes of non-equilibrium gliding, and these equilibrium points, they organize the velocity polar diagram, as well as the initial pitch angle and jump velocity determine glide performance. And as Jake mentioned, this was published last year in Bioinspiration and Biomimetics. Okay, so now let's talk about the snake. So this overhead view shows that as the animal glides forward, it uses this large amplitude side-to-side motion. So in effect, it's turning its whole body into a morphing wing. And at each instant in time, we can pull out key features of the snake's morphing wing body. So it's got these long, straight segments that are nominally perpendicular to the flow. And these are connected by what we call U-bends. And then as the animal glides forward, it places a new straight segment at the beginning and then passes all these features down its body. So not only is it morphing because it's undulating, but the shape actually, the snake changes its body shape. So the first 3 quarters, they flatten into this roughly triangular shape. The last quarter is the tail, and it's kind of circular. So you're familiar with animals that undulate on land and in water, but flying snakes are the only animal to undulate through air. And because the physical medium is different, we expect the physical implications of undulation to be different. And I can think of 2 key ways. The first has to do with force production. So to glide successfully, the snake needs to produce lift and drag to offset its weight and to pull it over the ground, so horizontally over the ground. So if the snake's kind of undulating in this plane, those forces are going to have to act out of the plane of undulation. But it's not so with the other animals. And because the snake is in air, it has to deal with rotational stability. And there's a couple aspects of this. So it's got these out-of-plane forces, which could cause it to pitch or roll to the side. So it's undulating, so it's redistributing how these forces act on its body. And it's also moving mass around, so there could be some inertial effects. And for the other animals, it's not the case. So once they stop undulating, locomotion stops. It's not really interesting. So for this section, I'm going to try to answer what is the mechanical role of undulation on gliding. And to do this, first I'm going to talk about some glide experiments, so we can answer what is aerial undulation, or what's the snake's body doing in the air. And that's going to enable me to build up an analytical model of snake flight. Now we can ask questions such as, well, is undulation required for gliding? How does body posture affect performance? And also, what is the relative role of aerodynamic and inertial moments on the stability of the system? So I'm starting with experiments because this was our previous best understanding of flying snake kinematics. It was 5 points placed along the body, and when you try to reconstruct the morphing wing, you could see that really we can't. We don't know what the animal's doing in the air. So to address this, we went to the Moss Art Center here at Virginia Tech in a portion known as the cube. So when you step inside the cube, you see it's a large black box theater. And what makes it a great facility for us, besides its size, is it comes in-house with a high-speed motion capture system. We can place the highlighted in blue here. As we can place our own high-speed cameras there as well. That's exactly what we did. So we use a 23 camera motion capture system at 179 frames per second. We placed cameras in the facility where we thought the snakes would glide. And then we placed between 11 and 17 infrared markers along the dorsal surface of the snake to record its body. So this is what comes out from the motion capture system. So here's a glide. It's got 14 markers on its body, each a different color. And from the top and side view, you can see as the animal glides down, right, these markers make a nice interweaving pattern. And in that case, we recorded about 8 meters of fall and 4 meters of horizontal travel. So from the infrared marker locations, we need to reconstruct the snake's body. So first, I fit a spline to this. So this is now a continuous representation of the backbone of the snake. So from this spline, I can extract a tangent vector. This is a unit vector that's locally tangent to the body, and it points from the head to the tip of the tail. And this encodes all the information about aerial undulation that we need. I'll discuss that in a bit. So the snake is a wing, and wings have an orientation. So I'm going to take the width of the animal and use that to define the chord line. That's going to give us this unit vector C hat here in red. And then it also gives us this B hat unit vector in blue that points out the top of the animal. So this is a local coordinate system that twists and bends depending on the instantaneous configuration of the body. So next I add shape and mass to the spline. So I measure the width of flying snakes in their mid-glide posture from silhouette images. And you can see it's roughly parabolic and it peaks midway along the body. And next I added mass to the spline. So by using snake sectioning, so we actually cut up small sections of the snake and weighed them, and you can see it's roughly parabolic as well, peaking in the center. And then I overlay these on top of the spline. So this is what comes out at the end of all of this processing. So here's one of our glides, an overhead view. You can see the snake's jumping and it's forming the S shape. But now you can see we have really an unprecedented level of detail as to what the snake's body is doing in the air. You can see it's much more complicated, right? It's got this consistent vertical motion. Positive here, you can see at the U-bends, the snake's cross section is kind of twisting and bending. So it's a lot more complicated than simply an S shape. Here's another one of our glides. So this is our lightest animal, and this was the glide that would have gone the furthest, but it landed on a tree we had set up in the facility. So once again, so it jumps out, it forms the S shape. But visually, you can see that this is a much tighter shape. And then if you look from the back, you can see that this snake, in this case, it has a considerable out-of-plane motion. Right? So this is where the tail starts, and it's falling very far below the head. Let me just play that one for you. Right. And then you can see, once again, a very tight body configuration. So we have 36 trials with that level of detail. So what I did is I quantified that complicated three-dimensional body position using two waves of bending. So we have a horizontal wave and a vertical wave, and these are based off of the tangent vector from before. So visually on the snake, the vertical wave, it's the angle the tangent vector makes down from the horizontal, and the horizontal wave is the angle the tangent vector makes relative to the back of the snake. So on the left, this is a movie of those two waves of bending, and on the right is an overhead view of the spline. And this is for that first glide that I showed you. And you can see that after an initial transient, that consistently two waves of bending set up on the snake's body. So we have this large amplitude horizontal wave and the smaller amplitude vertical wave. And although from the video it looked like the vertical motion was kind of random, this shows that no, it's very consistent and it's tightly coupled to the horizontal wave. So looking at one time point, we can pull out some key features of aerial undulation. So first is the vertical wave has twice the spatial and temporal frequency as the horizontal wave. So there's twice as many bends in the vertical direction as the horizontal. We have zero crossings of the horizontal wave. Well, those are the U-bends on the snake. And those correspond to peaks in the vertical wave, indicating these two waves are phase shifted by 90 degrees and that the maximal out-of-plane bending occurs at the U's. And so the effect of this on the snake, well, it causes the local cross-section to twist and to bend. So it's an additional level of complexity to the wing body of the animal. So I quantified how consistent this wave coupling is using a technique called complex orthogonal decomposition. It's like principal component analysis for traveling waves. So I'm showing here on the y-axis is the temporal frequency ratio of the vertical wave to the horizontal and the spatial analog on the x-axis. And when we look at all our glides together, we can see this frequency ratio is 2. That's consistent. It's interesting to note sidewinders, which you just saw, they use 2 waves of bending, but their frequency ratio is 1. So as far as we know, flying snakes are unique in this regard. And then I further quantified the average wave properties. So first is how the horizontal wave amplitude varies with a number of spatial periods. So this was the only significant relationship we found, and it was an inverse relationship. And to give you an idea of what these mean, so the square here, that's for the second glide you saw, so that was the lightest animal that went the furthest. The triangle, that was for the first glide I showed you. Next is the vertical wave amplitude. So there was no significant relationship here, just simply that the snake always has a vertical wave present, so it's never undulating completely horizontal. And then there's a third component, which I quantified as the slope to the best fit line of the vertical wave. And I termed it dorsoventral bending, or you can think of it as out-of-plane motion. And it's really quantifying this effect here, where the back half of the snake falls below or above the head. And once again, no significant relationship, just simply that there's both negative and positive values that the snakes use. Okay, so now that we know what aerial undulation is, what effect does it have on the animal? So I'm going to propose these 2 analytical expressions for the 2 bending waves. And so you can pull off the amplitudes, the number of spatial periods, and this out-of-plane motion from our kinematics data. I'm going to couple these 2 together with that 2x frequency ratio. And then putting in representative values, these are the waves. And then we recover the snake's body by integrating the bending along the body. And then a traveling wave of bending results in aerial undulation. And you can see we have the key kinematic features. We got these long straight segments, tight U-bends. I added a head control in the model so the snake's looking forward. And then from the front view, you can see that we have maximal out-of-plane bending at the U, and the cross-section twists and bends. So from the kinematics, we have the location of each piece of body relative to a center of mass frame. So now we need to write equations for how that frame translates and rotates relative to an inertial coordinate system. So the translational motion is simple enough. We have F equals ma, where we have our lift and drag force and the weight of the animal. The rotational motion is a little more complicated, but on the left-hand side, we have aerodynamic moments due to the distributed lift and drag. And we also, on the right-hand side, have standard rigid body terms and what I call inertial moments. So these are moments that arise from the snake undulating, or redistributing mass about the center of mass. And then we have the kinematic differential equations for how the yaw, pitch, and roll angles vary with time. And standard aircraft oiler angles, so kind of yawing would be this direction, pitch, and then rolling to the side. And now we need forces acting on the simulated snake. So I'm going to use the quasi-steady assumption. And this states that the local force is only a function of the instantaneous velocity and orientation to the flow. So with this assumption, we can then use previously measured lift and drag coefficients for the 2D cross-section of the snake as functions of angle of attack and Reynolds number. And then to deal with the curved sections, I'm going to use simple sweep theory. So I'm only going to use the velocity component that's normal to the body. And then lastly, the blade element method. So we're just going to discretize the snake's body and find those forces locally and then integrate. So this is what comes out of the model. So on the left, you're going to see the rotational motion. You're going to see some sheets. Those are going to be the lift and drag force. And on the right is the center of mass in the side and top view. So our simulated snake, it jumps out. It picks up speed. So the velocity is this black vector here. It starts producing lift and drag force. See, it's undulating, so it's kind of redistributing these forces. It begins to oscillate here. But eventually, the center of mass contacts the ground, so we stop the simulation. We say that was stable. So we can ask, what if you turn undulation off? So these are a simulated snake glide, exact same initial conditions, just no undulation. So it jumps out, it picks up speed, starts producing forces, but very quickly it goes unstable. In this case, it pitches down and then rolls to the side. So it exceeds an angle threshold, so we stop the simulation and say this was unstable. So we can conclude that undulation is increasing the rotational stability of the system. And this is clear if you look at the Euler angle. So without undulation on the left, we see just a secular trend away. So it starts pitching and rolling, there's nothing to correct it. So on the right, with undulation, we see that these angles now become periodic, pretty close to 0 degrees, which would be our stable condition. And the pitch angle is periodic, but we see this general pitching down trend. So there's a slight pitch instability. And this arises due to the aerodynamic moments. So now we can look into our equations of motion. So these are aerodynamic moments about the pitch, roll, and yaw axes. And we can see on average about the roll and yaw axes, the moments near 0. And about the pitch axis, in this case, we have a net negative pitch moment acting on the snake, and that's what caused it to pitch down. And I'll discuss this more in a little bit. So now we can explore the model further, right? So we found this relationship here for the horizontal wave of the snake. So what effect does it have? So what I did is I took this space and I discretized it. So now we have 121 candidate snake shapes. I call this the horizontal wave shape space. And you can see here that the snakes only use a certain section of this space, right? So we have these visually open shapes snakes don't use. They use shapes along the diagonal, so each box is a measured body shape in our animals. And then we have these visually closed shapes in the upper right. And so what I'm going to do is for each candidate shape, I'm going to simulate a glide both with and without undulation and look at some performance metrics. I'm going to do that for short glides, like say 10 meters, and then long glides until everything goes unstable. So our first performance metric is going to be the height fallen before going unstable. In this case, no undulation, and now with undulation. In this case, a 10, we would say that was short-term stable. And what we can see is that undulation has a big effect. And so with undulation, all glides along the diagonal were stable. Only 35% of glides with no undulation were stable. The next metric is going to be glide distance over the ground. Once again, no undulation, and now with undulation. So the effect isn't as large here. But what we see is that without undulation, the simulated snake is still going to cover some horizontal distance over the ground. But when you add undulation, so open loop feedback, basically no other control, that increases to 4.9 meters. And depending on some shapes, so down here they only go 3 meters, and these are going 6, so it can have a pretty big effect. So we can conclude from this that undulation, it doesn't seem to be a strict requirement, right? The animal is still going to cover some distance over the ground, but by adding undulation, it's going to perform better, it's going to be more stable. It's also interesting to note, so with undulation, along the diagonal generally performs better than the closed or open shapes. And for the long-term glide dynamics, so I'm showing here is the increase in height fallen and the increase in glide distance due to undulation. So red means undulation is performing better. We see on average a 12.5 meter increase in height fallen and 6.9 meter increase in glide distance due to undulation. So we also have the vertical wave. So this was something we didn't know existed in flying snakes. So what effect does it have on our modeled system? So once again, we're going to do a parametric sweep. So for the vertical wave amplitude, it's going to be 0 degrees. That's going to be completely horizontal undulation. Then we're going to increase that to greater out-of-plane undulation. And for the out-of-plane motion of the snake or dorsiventral bending, we're going to do negative and positive values. So that was what was seen in the kinematics data. And instead of using the whole horizontal wave shape space, I'm only going to sample along the diagonal that was observed in our kinematics. So I'm showing you here, this is the center of mass position from a side view for our simulated glides. The different colors correspond to the horizontal wave. And what do we see? Well, if you go down a column, so that's going to be fixing the out-of-plane motion of the snake and changing the vertical wave amplitude. We see it not a lot's different, right? So up here, these glides are unstable. So some of these down here more stable and they perform a little better. But the effect there is the vertical wave. It's changing the orientation of the body to be more aerodynamically advantageous. We see a large effect if you go across the column. So if you fix your vertical wave and you change this out-of-plane motion. So we have this tail-down configuration here on the left. So these glides, as I said before, those are unstable, right? They don't reach the ground. We see the performance peaks here, in this case, at 10 degrees. So all these glides are stable and performance is best. But if you go too far, in this case 20 degrees, they're stable, but they're performance is bad, so they land, in this case, some of them behind the jump location. And so once again, this is due to the pitch dynamics of the system. So this tail down configuration, which was unstable, that's associated with very strongly pitching down. The 10-degree case, pitch angles are closer to 0 degrees. But then this 20-degree case, their pitch angles are positive. So the simulated snake jumps out, it pitches up, and then gets pushed back. And this, once again, is due to that pitch moment. So what this tells me is that this out-of-plane motion can function as pitch control. So what I'm showing you here is the net pitch moment on the simulated snake for the different out-of-plane motion. And so if you want to control pitch, you need to change the net sign of the moment acting on the system. And so if you're to fix where you are in the horizontal wave shape space, that's going to be picking one of these colored lines. And if you're to change the dorsoventral bending, you're going to move along like this. And you can see we can change the sign at that moment. So alternatively, you could say, well, I'm going to fix my out-of-plane motion. So that'd be picking one of these lines here, and then move around in the horizontal wave shape space. And you can see you can't really affect in that pitch change. So this suggests that this out-of-plane motion is to control that pitch instability. And it also, the snakes themselves, they have a lot of mobility in this direction. And then lastly, we're interested in the relative role of aerodynamic and inertial moments. So you've already seen the aerodynamic moments, so we can look in our equations of motion and pull out the inertial moments. And to quantify this relative role, I'm going to take the peak-to-peak ratio and how that varies throughout the glide. So first, about the pitch and roll axes, we see initially inertial moments dominate, but then within one undulation cycle, they become comparable. So you can't ignore inertia for this system. About the yaw axis, we see that inertial moments always dominate. And so they're always an order of magnitude greater. And this is due to the large amplitude horizontal wave, or the S shape of the snake as it glides. So what I think this suggests a turning mechanism for these animals. So there you just saw the snake execute a yaw turn to the left. I think what it can do is bias its undulation to take advantage of that large inertial yaw moment and reorient its body. Okay, so from this section, we now have our first full 3D understanding of the flying snakes, a snake body in the air. And I use that to build up our first anatomically accurate model of snake flight. And so from our original question, undulation is enhancing the stability, enabling gliding in these animals. And they do appear to use the undulation differently than other long-bodied animals. So some specific takeaways: we found aerial undulation consists of these two waves of bending and this gross out-of-plane motion. We found only certain horizontal wave shapes are used, and they generally resulted in better performance and stability. And lastly, this out-of-plane motion of the snake is like a pitch control mechanism. And this manuscript, we're going to submit it to PNAS in the next few weeks. So for the third section, so this idea that the snake is a morphing wing. And well, if it's a wing, we'd like to know how effective it is at producing lift and drag. Right, so that's going to determine the performance as a glider. Related to this is also the relative role or the relative spacing of the body throughout a glide. All right, and this could affect, and does this have an aerodynamic consequence? So what I'm going to be testing in this section is if the quasi-steady assumption is sufficient to explain force production in flying snakes. Now this assumption, it's been tested for flapping flyers and it's been found lacking. And this has prompted really a lot of interesting aerodynamics work looking at unsteady and three-dimensional mechanisms that animals use to move through fluids. And as far as I'm aware, it's not been tested for gliding animals. So it may be applicable because they have a relatively static body configuration, so there's obviously not a flapping wing. And it may be applicable for the snake for a couple of reasons. First is a separation of velocity scales. Right? So the snake is undulating, but the speed of undulation is relatively slow compared to the speed of forward flight. And then additionally, there was a analysis done, and they found that glide performance, so several glide performance metrics were not related to undulation frequency. So it's not like the snake was undulating faster and gliding further by producing more lift. So we can test this now. So here's our snake at one time point, and we now have an estimate for the lift and drag distribution, so from our kinematics and our aerodynamics model. And at the center of mass, we're, once again, F equals ma. So we're going to have the resultant aerodynamic force on the left-hand side, and then the acceleration of the center of mass on the right-hand side. So I can check quasi-steady theory because, well, now we have an aerodynamics model, so we can calculate the lift and drag force. But equally important, we have the right-hand side. So we now know where the center of mass is, and we can calculate its acceleration. So this is the quasi-steady predictions. These are for 33 trials from 3 individuals. And these were the individuals that gave us the greatest number of glides. And they also span our mass range. So I'm showing you here, this is the lift and drag force, acceleration and gravity on the right, the 3 different snakes, and this is the force in the forward direction normalized by weight. And what we see is that quasi-steady theory, it's under-predicting the aerodynamic force from what we'd expect based on the accelerations. About the vertical direction, it's the opposite. So quasi-steady theory, it's over-predicting force compared to the accelerations. So this is clear if we look at the errors. So this is the absolute error. And about the lateral direction, we see it's about 0, so that's good. About the forward direction, we see we're off by up to a quarter of the body weight. And about the vertical direction, we're off by about a half the body weight. So this tells us that quasi-steady theory is resulting in high errors, and there's likely something more interesting aerodynamically happening for the flying snake. It's also interesting to note these errors are consistent for the different trials and different individuals. So that consistent error prompted me to see if we could determine how it's failing. So what I did is I said, okay, we're going to keep the orientation of these forces. We're just going to scale them to minimize the total error. So basically, we're going to keep the orientation of the force and just change the lift and change the drag. So these are the required multipliers for the lift force. And what we see is that initially it starts off high, and then it decreases during the glide, but the multiplier, it's greater than 1. So we need to enhance lift from what the quasi-steady theory predicts. And so quasi-steady theory, it's under-predicting lift by about 35%. And for the drag force, we see here, in this case, the multipliers are less than 1. So we need to, in this case, it's quasi-steady theory is over-predicting drag by about 40%. And these are consistent throughout the glide. So ultimately, we need to increase the lift-to-drag ratio from what quasi-steady theory predicts. Now, one reason it could fail, it's been recognized previously that there can be these wake interaction effects for flying snakes. So in that case, we can't ignore the time history of the flow. And so for this shape here, you can get an enhancement of 50% in the lift-to-drag ratio. So for Reid Jafari, he tested this extensively for his PhD work, and he found that for the flying snake cross-section, if these are really close together, you have the greatest wake interaction effect, but also in snake-like configurations, you can also experience a modification. However, they had to estimate these configurations based off of the previous kinematics data, where we really didn't know what the body was doing. So from my data, we can now measure the body spacing. So what I did is I took the snake and I rotated it such that the center of mass velocity is in the forward direction. So its body's going to rotate and the flow is going to go like this. And then I took a vertical plane at the center of mass. This is a vertical plane. I'm going to find intersections of the body with that plane. And so from those intersections, I'm then going to take gap as the relative horizontal spacing and stagger as the relative vertical spacing. And then each of those intersections, it's going to have its own velocity, angle of attack, and sweep angle. So here are the gap and stagger distributions. And the way to read this, so I've broken these down based on progress through the glide, so the first, second, third, and fourth quarters. The front airfoil is going to be this red dot. So every other location in the space is the trailing airfoil. And so for these yellows, so these yellow markers, the intersection, that's the median of those distributions, so the median gap and stagger, and then the first and third quartiles. And what we saw was a little unintuitive. So initially, the body's kind of angled this way, like we'd expect, but as the glide progresses, we end up in this configuration here. So this is kind of like the biplane configuration as opposed to the airfoils directly behind each other, or one behind the front. And so this is now the measurement locations that for Reid looked at, and then the greatest wake interaction effects here. And what we found is we really don't record many glides that have the body in that configuration. So I don't believe wake interaction effects explain the failure of quasi-steady theory for our glides. Using this analysis, we can then look at some other quantities. So in this case, how the sweep angle varies during a glide. So initially, sweep angles are high. So this is as the snake is forming the S shape. But even later in the glide, you see that sweep angles are high. So the snake is always acting as a swept wing. For the angles of attack, they're also high. So initially, they start out at around 75 degrees. But then as the glide shallows, they decrease to about 60 degrees. So from this section, we can conclude that quasi-steady theory was insufficient to explain forces in flying snakes. We tested if wake effects could explain this failure, and we found that doesn't seem likely. So this tells me that unsteady aerodynamic effects are going to be important for flying snakes and an area for future work. And then we also have new test configurations, so empirical distributions for gap, stagger, sweep angle, and angle of attack. And this work is going to be submitted to the Journal of Experimental Biology later this semester. So I think an important step in the future would be to take my kinematics data and try to understand why quasi-steady theory is failing. So we have a collaboration with Haibo Dong at UVA, and he specializes in taking in these moving meshes of animals, which is basically what we have from our kinematics, and then running them through his CFD pipeline. So this might help explain if there's any unsteady mechanisms and what those are, where they act on the snake's body. So in summary, so these are the academic contributions for my PhD work. So these are the 3 manuscripts I discussed today, and there's a 4th one talking about how these animals can land, which is really interesting work, but I didn't have time to talk about. And then, as Jake mentioned, some presentation awards at different conferences. So with that, I'd like to thank my PhD advisors and my committee for your help doing this work, as well as Soha Lab members and Ross Lab members for helping conduct experiments, as well as think through how to analyze data and what it means. So thank you.
Are there any questions from the audience?
When you show like the diagonal of the actual snake body shapes,
Yes.
you know what I'm saying? How
Yep.
did you? How is it like? I assume that since the snake's body is moving a lot, how do you like decide which
Yeah.
one is a like representative shape?
All right. So this here.
Yeah.
Yeah, so the way I did that, so obviously the snake's body, it changes during the glide, right? You just saw that like sometimes the back half falls down, sometimes it's horizontal. So this was that complex orthogonal decomposition. So we have how those bending angles change with time. It's basically a way to say, okay, for this glide, what's the average shape that it used? So that's how I picked these shapes here. So yeah, I think future work, so if we had longer glides, there may be a way to determine how the snake, it moves around in this space here, as well as all the vertical wave and the dorsoventral bending. So that, I think that could be, if we had the data, we could look at
So
that.
it's like for a given glide, the gray boxes represent like the dominating or like the average shape.
Exactly. Yeah, and so for the ones I showed, like it was this one and this one here, you can see visually those looked quite different, even though those changed during the glide. Yes.
I've always assumed, I don't have anything to do with physics or anything, but I would imagine that wake forces would be very destabilizing for flight. So it's difficult to imagine that any type of structure in which you've had a second foil in a wake would be contributing in any way to stable flight.
Yeah,
Is
so
that, I don't understand why you would be.
yeah,
looking
so
at that.
so for the animal we're more interested in, it does it modify the forces? So it may be destabilizing, but we don't know. So if it is there, yeah, it could impart a moment, say, cause it to pitch down or pitch up. So the snake might have to deal with that, but it also might enhance the forces on the body. So giving like a boost in lift, so shallow out the glide more. So it may be destabilizing. It's something it has to deal with.
But there aren't any instances where the snake intentionally avoids wake forces in its shape.
So that we do not know. So that's, I guess, one of the ideas, like, could it configure its body to take advantage of that, or like you're suggesting, like, avoid those regions? Yeah, we don't know. I have a feeling that it doesn't have the sensing mechanism to determine that. Like, it's just going to do what it does. Yep.
Do you think that the high sweep angle that you find in the data may have something to do with three-dimensional wake structures?
Yes, probably. I mean, I think there's going to be some span-wise flow possibly down the body. The body's always accelerating, so a span-wise flow and accelerating, there could be like a leading edge vortex, something like that. But yeah, we'd have to test that in the lab or CFD to see what's there.
Did you try to find how they are turning?
No.
No. In gradual motion of snake, if you add just a constant parameter to your theta at the end of that equation, it causes them to turn
Yeah.
to right or left.
Yeah, so that's interesting to note for what I was saying. So if you instead of put this constant, if you were to put it up here, you can use that to like turn a snake robot or a simulated snake. It kind of changes the horizontal wave and causes them to turn. I don't think they're doing that. I don't think it's that. I think it is the inertial effect. So it would be, as I showed here. There would probably be inertial yaw moments, I think, to reorient the body. And then to how it actually does that, or how would we control that in the model, that would have to be future work. Yep.
Your equations of motion consider like internal body moments, or is that kind of worked out in the?
Yeah, no, those cancel out for the rotational motion.
Oh, they did.
Yeah, so I just simulate how the body, the position of the body, not the underlying muscle activation patterns, or like a wave of torques that you would need to get that shape. So we're just saying prescribing the shape. Yep.
The dorsiventral flexion that you talk about is really interesting because it seems like they can use that for some sort of pitch control. Have you looked at how that dorsiventral flexion changes with time over the glide?
I have not specifically.
Okay.
I've looked at a metric called sinurosity, which is basically the distance between the head and the vent.
Okay.
And I mean, it starts off high and then it goes low, but I didn't see anything consistent between like a lighter snake that performed better. As it said, if we had longer glides, so we were able to piece together how they're time varying the dorsiventral bending and the pitching motion.
Other questions? All right, let's thank Isaac again.
How long did that go?
I don't know. I think you're perfect. Yeah. Does anyone need to take a break?
Yeah.
Let's take exactly 5 minutes.
Very nice work.
Mm-hmm.
You got that on tape? All right, so I can't fail it now.